Okay, so this is, who's not here today that we could give a shout out to? So, should we put a code word in the video? Code word in the video. Hanky never watched his video, so he never got it. Yeah, whatever. What did he say? Oh, he did. That's right. Yay. Yay for Gavin. All right. Okay, so what's the code word for this group? What are we going to make them say? What's that? Oh, golf is bad. Wow. They would have to say golf is bad. They're all kind of little golfers running around doing their thing, right? How about this? How about this? We won't make them say golf is bad because how about we say this? They have to come and say, I wish I could go run a mile. How's that? Yeah. If you come in and say, I wish I could go run a mile, then we will give you the reward of, yeah, Little Debbie snack. So, Gavin, we owe you one. Okay. Oh, I don't eat that. I'm like Mr. In Shape guy, so I don't know. Yeah, whatever. Nobody asked you to talk, Luke. Okay. Definition of a parametric equation. Equations that are dependent upon a shared parameter. Parametric equations are equations that are dependent upon a shared parameter. So, let's try to unpack that and understand what it means. Everybody see I have two equations here, an x equals and a y equals, and they have a shared parameter, meaning a shared variable. What variable do they share in common? They share t. Normally you guys are used to seeing equations that have x and y in them, right? And this one has t involved in both of them. See, sometimes there's a third variable involved in situations and allows us a lot of options for graphing. Parametric equations are very powerful as we try to produce all sorts of graphs. So I want you to think of this. Suppose we have, let's see, do we have a baseball player in here? Softball player? A golfer? They're all gone today, huh? Let's go, what's that? Oh yeah, we'll use Sid. Sid's throwing, okay? So Sid's going to throw. She takes that disc and she winds back. She's doing the spin. She keeps the circle tight and she releases. And all of a sudden, disc comes on out, okay? As the disc releases, is the horizontal location of the disc changing? Yes. And is the vertical location of the disc changing? There's another variable that we're not talking about that's changing as well that relates the two together. Speed would be one, but time would be another. As time goes by, the horizontal and the vertical location changes, right? So many times this shared parameter is t for time. And that's something that is, as you understand, is very applicable in physics and in lots of applications. And so that's why parametric equations become very important. So what we're going to do, and this will be one of the questions on your test where you'll need to be able to generate a table, and via that table you have to produce a graph. So are you able to plot points and plug things in? Good. Sounds like you should be able to get this question right then on the test. So -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. What? So in this case, I'm going to graph this for a domain of -3 is less than or equal to t, which is less than or equal to 8. So the nice thing about parametric equations, you're able to control the time frame under which they are mapped as well. Sure, you could say seconds or something. So we'll say -3 seconds to 8 seconds. Okay. Obviously, in many situations, we start with time is equal to 0. That would make sense, right? We're just, making something else up here. No big deal. But I'm going to define -3 to 8. As you can see, this one down here is defined from 0 to pi. Okay. So you have all sorts of different options there. So, all right, let's plug it in. -3 squared minus 3 times -3. That would be +9 minus 3 times -3. 18, very good. right, I plug in -2. I would have -2 squared is 4. Is it then going to be -6 or +6? +6, which is 10. -1 squared, 1. And then is it going to be +3 or -3? +3, which is 4. What do you get when you plug in 0? We get 0. And when I plug in 1? -2. Very good. We're going to plug in 2 now. I have 2 squared minus 6. -2. Then I plug in 3. 3 squared minus 9. 0. 4 squared is 16 minus 12. 4. 5 squared is 25 minus 15. 10. What do you notice is happening? Yeah, it's going back up. So the next one you can see is going to be 18. If you plugged in 7, you would get 49 minus 21, which is 28. And then 8 squared is 64 minus 24 is 40. Y'all good with that? No big deal, right? Could you do that on the test? Sweet. Yep. Very good. So now we're going to determine the y values. How do you determine y? You take t minus 1. So I have -3 minus 1 is -4. I have -2 minus 1 is -3. I have -1 minus 1 is -2. As you can see, it's just going to continue on like so. All good with that? All right. So when we graph it, you don't graph t. It's still just an x-axis and a y-axis. And it can produce a shape that we are, familiar with or unfamiliar with. Let's see what we get. I'm going to go ahead and take my x values. It looks like I go all the way to 40, so I'm going to make this 40. And then it looks like my y value is going from -4 to 7. So I'll go all the way up to 8 here. Any questions how I've produced my graph? All right, so I ignore t and I plot x, y. So x is 18, y is -4. X is 10, y is -3. X is 4, y is -2. X is 0, y is -1. You're not stupid. What shape do you get? Yeah, it's a sideways parabola. Now here's what's interesting is you're able to control the beginning point and the ending point. Okay? So we don't, with the normal parabola, we just put arrows on the end, right? But in this situation, you start at -3, which gave you this value, and you stopped at 8, which gave you that value. So you could chart the exact motion. Picture this, if you would, for a second. A figure skater that is skating all around the ice arena during a routine that lasts 2 minutes. You could actually come up with parametric equation to map that exact motion over the course of whatever time period you wanted to use and be able to control it perfectly. So, I mean, that's some of the operation and application. And is that things that people would keep track of? Well, sure it is. You could track things that are moving through blood vessels throughout the body and actually determine exact equations for it. And if we just add another variable in there, z, we could also locate three-dimensional spaces as well. So it's pretty cool and powerful. We just do kind of a one-day basic lesson. But let's take out our calculators and see how those are impacted by these parametric equations. The first thing I want you to do is I want you to click on Mode. And just to be clear, this is something you'll be expected to do for your test. So you'll be expected to know how to use your graphing calculator and plug in equations. I think that that's a reasonable expectation. Nope, we got an unreasonable one over here. Okay, so first of all, we will work in radians. Second of all, as you move down, you can see function, you can see polar. We are going to choose parametric option right now. Parametric option. I press enter on that. For some reason, which I'm not sure, as I press y equals, there were people that had their plot turned on. If your plot is turned on, please turn it off. Just go up, highlight it, and press enter, turn it off. And I type in t squared, so this is my variable, so I get t squared minus 3t. Okay, so time out real quick, everybody. Let me explain this. When you guys type x, do you type the x right here? Okay, so the x, x, t, theta, n, they're all right here. This is your variable. Press it. If you're in parametric mode, it will put t. If you're in polar mode, it will put theta. If you're in sequential mode, it will put n. If you're in rectangular function mode, it will put x. So go up onto plot and press enter, and that will turn it on, or go up and press enter, and it will turn it off. Okay, now let's do the next part. I'm going to do t minus 1. Now, I don't like the window that it's sitting in, but to make sure that we're all under the same graphing constraints, let's make sure that we do this together. I'm going to press zoom 6 or zoom standard so we all get the same kind of window. Now, this is not the graph that I want because it started at time 0. I want to start at time -3. Furthermore, it went on for who knows how long. I want to stop at 8. So press your window and I'll show you how to control that. It says, what is your t minimum? What was our minimum value for t? So I type in -3. What was our maximum value for t? 8. This is a t step. It's like how often is the next step before it plots. Just leave it alone. Don't worry about it. I'll show you what happens with t step later on. You'll get an idea. But right now, just leave it alone. X min, I'm going to go -20 on my graph. For x max, I'm going to go +40. And then for a scale, I'm going to use for a scale 10. For a y minimum value, I have -8. And then for a y maximum value, I have 8. And I have a tick mark every 2. So now, when I press graph, hopefully it starts it at exactly that location, and then it chooses to end, hopefully, right there. Actually, I'm going to change my x max value to 50 just so we can make sure that we see that it ends. I press graph, and look at the shape that I get. Exactly what I wanted, right? So if you change this, which is kind of cool, if I go into my window and I change my t max, let's say I change it instead of 5, let's say I go 4. Well, now watch it. It will stop it whenever the 4 spot is. So you can control exactly the portions of the graph that you want. And also, we were able to graph something that we said is not a function. It does not pass the vertical line test. But yet, through parametric functions, we are able to, which makes graphing have endless possibilities. Now, I'm going to go back in my window, and I'm going to change it to a t max of 8. But here's what I want to show you. Watch what happens when I change the t step. I'm going to change it from 0.13. I'm going to change it to 0.05. Tell me what's different about my graph. It's slower, isn't it? It's actually plotting maybe more points and it's slower. Watch what happens when I go to my window and I change my t-step. I'm going to change it to 2. See that? So the t-step is kind of like your step in time. Does everybody agree that 2 steps in time is quicker than like 0.5 steps in time? You get my point? So if I change that back to like it was at like 0.13, if I change it to 0.1, that's generally a good number to be at as you kind of try to pick stuff up. Okay. So everybody okay with the graphing option? We're going to give you more practice with it, but first let's go to the second part. It says write an equation for the parabola by eliminating the parameter. By eliminating the parameter, we mean putting it into rectangular form. So right now it's in parametric form, and parametric form is of the form t, x, y. We want to take it from that form and we want to turn it into the xy form. So all we have to do is get rid of the t variable. Notice I have x is equal to t squared minus 3t, and I have y is equal to t minus 1. Can anybody think of something I could do to make t go away and only have x and y? Yes, Luke? Yep, so if I have y plus 1 is equal to t, if I solve for t, get a y plus 1, I could take the y plus 1 and I could drop it in for t there and there. And now I have x is equal to y plus 1, quantity squared, minus 3 times y plus 1. So x is equal to, what happens when you square y plus 1? Y squared plus 2y plus 1, good. Minus 3y minus 3. And as we combine like terms, I get x is equal to y squared minus y minus 2. And as you notice, what shape does that make? A parabola. Right side up, upside down, or is it left and right? Which is it? This is a horizontal parabola, and it heads off to the right, doesn't it? And that's exactly what we have. In fact, you can even see it should have an x-intercept of -2, and it goes through the x-axis of -2 right there. So we have eliminated the parameter and turned it into rectangular form. All right, so be ready for that kind of a problem on your test. The next thing you're going to have to be able to do is you're going to have to be able to plug things in and just describe the general shape. So let's plug these in. We go into y equals, and I'm going to graph 3 cosine of t, and I'm going to graph 3 sine of t. And we're going to see what kind of equation we get. Before I go to this parameter restriction of 0 to pi, I'm going to zoom standard. I'm going to zoom 6 and see what I get. Somebody describe the shape for me? It kind of looks like an oval, but it's misleading because your graph is out of whack. Notice it goes up 3, down 3, side 3, over 3. If it's 3 in all directions, it's not an ellipse, it's a circle. Watch if I zoom as a square. Now all of a sudden I do get a circle. Everybody agreed? Yeah. Okay, so I'll go back to zoom standard, and so we see this, but this isn't exactly what we want. What we want is we want to go from 0 to pi. So I'm going to go into my window, and I start with a t-value 0, and it always defaults to going to 2 pi. We're just going to go to 1 pi, so I go second pi. It says x is cosine. Yes? No? So like when I have y equals, I have 3 cosine. Or x. Okay, if you press mode, are you working in radians or degrees?
It looks like a long,
Okay, let me quick pause and look at what's happening with. Okay, so they didn't press zoom standard to get back to their normal viewing window. That was our issue. So now, if I go 0 to pi, what shape do we get? It's not a circle. It's a semicircle. Yeah. Semicircle. And you know, if I choose to zoom as a square in this spot, how did I get this picture? I press graph. Oh, to get so you don't have the whole circle. Yeah, so you gotta go from 0 to pi. So in my window, I have my T max is pi. So that way I just get half of it. And I'm going to zoom as a or zoom as a square, and when I do, you can see that I do get just half that circle, don't I? You can see it's a circle. Now, here's what I think is kind of cool to show you the control that you get. Look, if I go into or if I go into my window, suppose I want to show 3/4 of the circle. Then I just do 3 pi divided by 2. And 3 pi over 2 should bring us all the way down. Sure enough, when you graph it, look at what I get. It just stops it right there. Or you could even change it, say window, I want to go from, say, pi over 4. And I want to go to 5 pi over 4. And look at what your graph does. Gives you just those portions. Okay? So it can really control any element of the graph that you want. So if you zoom 6, if you zoom in a standard viewing window, okay, what happens is that it stretches it sideways. See how it doesn't look like a circle? Because your window is longer than it is tall, right? So when you press zoom square, it makes an adjustment so that it actually looks like it's the same in all directions. You can do that. Okay, flip it over. What I want you to do is I want you to plug in these. We're going to go from 0 to 2 pi. And I would like you to graph them and describe the shape that you get. Okay? Try taking both of those, graphing them, and describing the shape that you get. Ready, set, go.
How do you become inspired on your
I'll show you. I got an ellipse. Is that what you got? Let's look at the bottom one now. If I try this one, let's see here. Okay, go away. And if I try the second one, I type in, everybody's wondering how to type this in. We just type in cosine of that value and we square it. Okay, we're just squaring cosine. And then you type in sine. And when I zoom standard and I try to, oh, I got a syntax there. I can press go to so I can see where it is. Looks like there's a second parenthesis. I'll delete that. Now as I graph it, I see that there's something happening here, but I can't see very much, can I? So some people have forgotten how to zoom with a box, and I'm going to zoom as a box. I press enter, and so I get to create my own box. I'm going to use my cursor, and I'm going to press enter to lock in the cursor, and then I can move down and over to make my box the way I want to see it. And press enter, and now I get a better picture of the shape. How would you describe that shape? Yeah, I would say it's a parabola. Facing left. You know, you could say vertex at 1, 0, you know. Give a nice description of what we're looking at. Okay, we'll try it again. So I'm going to zoom 6. So this is what I'm looking at. And then I will, let's see, I'll zoom as a box. So I'll move my cursor up to where I want the first corner of my box, and I'll press enter. And then I move down. It's not sine of t squared, it's just sine of t. And I move down and over, and I press enter again to hold the other corner in place. Better? Okay. All right. Last example. Okay. Here we go. We want to write a parametric equation for this line. So now we actually want to write an equation. You know how to write equations for lines. Y minus y1 is equal to what?
X minus x1.
M times x minus x1.
Times x.
So if I have a slope of 4 and it passes through the point of negative 2, 5, I'm going to have y minus 5 is equal to 4 times x plus 2. All right. This is rectangular form. We don't want this. We want parametric form. So we want something like x sub t is equal to and y sub t is equal to. That's what we want. So this is what you already know how to do. We want to write it in parametric form. It's not very difficult, just have to pay attention. There's a number of ways to go about this. I'm going to go ahead and just make a table. I'm going to make a table of t values, x values, and y values. And I'm going to graph that line. I'm going to go back 2, go up 1, 2, 3, 4, 5. So as the graph is created, I'm going to create my points. So I'm going to take this initial point right here, I'm going to call that time 0. Can somebody tell me what my x and y values are at time 0? Negative 2, 5. Because we plotted a point and it has the coordinate negative 2, positive 5. I'm going to advance 1 unit in time. I'm going to advance forward 1 unit in time. And I'll advance my graph to the next point. If we have a line that goes to this point, how would we get to the next point? Up 4 over 1. So since the slope is 4, we rise 4 and we run 1. So at time 1, what is our new location? I'll now advance another unit in time forward. How do I get to my new coordinate? I move up 4 and over 1. What's that? 0, 13.
More complex ways, just pointing graph like up and down function. Where's the
So we're running this amount. So we're running 1 and we're rising 4. Okay. If I advanced another, what would the x value become? 1. What would the y value become? 17. If you advanced another one, what would the x value become? 2. What would the y value become? Everybody see the x values are advancing by 1 and the y values are advancing by 4? Those are our slopes with respect to t. So, for example, for y, the slope is 4, so 4 times t. For x, the slope is 1, so it's just 1t. And then when t is 0, what is the x value? Negative 2. When t is 0, what's the y value? 5. So you could pick any point on here. You could say, well, let's check. When t is equal to 4, do we really get 221? Well, try it. If you plug in 4, you get 2 there. And if you plug in 4 here, you get 21 there. So this is a parametric equation because it has x and y dependent on t. When t is 0, x is negative 2. So when t would be 0, the x value here is negative 2. When t is 0, the x value or the y value is 5. When t is 0, y is going to be 5.
So as you go from point to point, you're increasing t.
Yep. I chose to increase it by 1.
Okay.
And the beauty is you could actually increase it by a half or a third or whatever you wanted to. There's actually an infinite number of representations for that line. This is just one. Please open up your worksheet so I can describe to you what you're going to be doing. Before life seems too overbearing, just understand that as of next week, Wednesday, you will have 8 days of mathematics with 2 homework assignments. That will be what you will have been given over the course of 8 days. Okay. All right. So notice that the first directions are sketch the graph of the following parametric equation, then convert the equation to rectangular form. When it says convert it to rectangular form, what I mean is what we did in our notes right here where it says by eliminating the parameter. Okay. So that's what that means. Turn it into x and y by eliminating the parameter. When you start graphing it, you notice that there is not a restriction given on time. I would encourage you to start your graphs as you're trying to come up with that graph. I would encourage you to start your tables like this. Time, x, and y. Start with time -2, -1, 0, 1, and 2. That's what I'd encourage you to do. That will probably try to help fit those appropriately. Come up with 5 points. That should probably be enough for you. We all good? You have time to work on this tomorrow in class. Good job, everybody.